Hey everyone, and welcome back to the ML India podcast. We've been on a bit of a hiatus and it's likely to continue for a variety of reasons. However, what I am excited to tell you about is this episode we speak with Professor Ravindran Balaraman from IIT Madras, who is a worldwide authority on reinforcement learning and graphs. This is definitely one of the best conversations we've had yet, spans topics from reinforcement learning, graphs, all the way up through to grad school in India. I hope you enjoyed as much as we did.
Professor, just for any listeners who are not aware about you, can you give like a small introduction?
Sure. Hi, my name is Ravindran, and I'm a faculty in the computer science department at IIT Madras. And I've been working in reinforcement learning, God, since 1994. And my primary research interest is in, looking at hierarchical reinforcement learning and all kinds of, scaling up issues with RL and looking at human in the loop RL and so on and so forth. I have been at IIT Madras since 2004. And I also head the Robert Pott Center for Data Science and AI at IIT Madras.
Okay, so to start with the first question, this goes back to me listening to your talk. So I remember in 2019, you came to IIIT Delhi to give a talk. At that time, I used to be an intern at IIIT Delhi, and a part of your talk was, and this is where I picked up this question from, that both the original backpropagation paper and a very early RL paper came in the same year, if I'm not wrong. And of course, both of these fields have grown tremendously, but we have seen a very large increase in deep learning. And there are factors like data there, that availability of data is more, availability of compute power is more. But why do you think, what led to deep learning being like a little bit more of a popular field, which students pick up a lot compared to reinforcement learning?
So this is not even deep learning, right? If you go back to the 80s, when in 83, both backprop and the first temporal difference learning, the first actor critic paper appeared, right? In fact, ironically, the very first reinforcement learning paper was something that used neural network. Right? So in modern day parlance, you would probably call it deep RL. So there was a deep RL paper before there was an RL paper. So what happened was, reinforcement learning for a long time, right, suffered from almost all the problems that deep learning suffered from in terms of needing a large number of samples and slow to converge and that doesn't really work well with function approximation. So you needed to have lookup tables, and therefore you had scaling problems, right? And there's all kinds of technical issues were there, right? They were plaguing RL, right? In the early days. And then even when people started addressing those technical issues, right, the biggest stumbling block was, even though there are a lot of like human learning problems which we or animal learning problems which we think are motivated by reinforcement learning, right? It turns out that if I'm going to look at some kind of industrial solution, deployed solutions and things like that, right, it turns out that supervised learning was a lot more amenable to adapt for solving real problems, mainly because the learning was mostly offline. And reinforcement learning, the classical method said that, oh, you needed to have a very detailed simulator, or you need to, put it out into the real system to learn from it, etc., etc. And so that was a huge stumbling block. You either needed a very detailed model, or you needed to be able to put things into the real world, right? And so that's still a huge stumbling block for reinforcement learning to take off in a big way, right? And so recently there's a lot of work that's happening on batch reinforcement learning, offline reinforcement learning, and so on and so forth, which could potentially address these issues, right? And yeah, and reinforcement learning is a harder problem in some sense than supervised learning to solve, and it took a while for us to get all the algorithmic pieces in place. And it's an accident also, right? I mean, there was like serendipitously, a lot more progress made in supervised learning at the very beginning than RL, and therefore one took over the other. In fact, a long time back, there were methods for training multi-layer networks that were proposed using reinforcement learning, right? But then that proved to be a lot more convenient, right? So the RL-based multi-layer network training algorithm did not need to do any gradient backpropagation. So they wouldn't have suffered from things like managing gradient problems, etc., etc. But then RL, the algorithms being data hungry and pretty slow to convergence back then, the training times would have been very long. Right? But so people actually gravitated towards doing this kind of backpropagation based update, gradient based updates, right? And then so this was kind of almost forgotten for a long, long time, literally. Right? This is not to say that RL was completely forgotten. In fact, reinforcement learning was picked up a big way by the people in the neuroscience community, in the behavioral psychology community, and so on and so forth, the temporal difference methods. So you did continue to see a lot of work come in those sub-disciplines, right? Those fields, actually. Even during the 80s and 90s, while it was slightly languishing in the AI side of things. Literally, there were like 4 labs in the world that were doing interesting RL back then, from a CS point of view. But then there are so many other bio or neuroscience labs that were looking at RL. So they took slightly different paths. But right now, I think a lot of issues are kind of commingling, and RL, or at least reinforced kind of methods are now used widely for looking at optimizing hard to compute gradients in the deep learning setting as well. And of course, all the function approximation and fancy things that you could do with deep learning is helping RL to grow even faster. So that one bottleneck, right, that the whole function approximation bottleneck was solved, somewhat solved by using deep architectures, and that certainly helped RL to pick up. Right? So it's like just a combination of factors culminating and RL becoming better now. So that's my take on that. Yeah.
So I mean, tapping into something that you mentioned, right? You talked about how RL it found a home in like the neuroscience fields, right? That's actually something that we want to talk about. Is that, can you tell us a little bit about some real world problems where RL shines? Because like we've already seen like the protein folding and stuff that DeepMind is like pulling out, right? And that seems like miraculous. Can you like expand a little bit about that, or like talk about like some real world issues which RL is like defit for?
So so reinforcement learning, before you got into all this, protein folding and other things, right? So people were trying to use reinforcement learning in as a tool for online learning, right? So all this kind of contextual bandits kind of setting, right? Which did use a lot of RL ideas in building things up. Right? So that is one part of it. And more recently, we have had a tremendous amount of success in looking at RL for optimization, combinatorial optimization problems, as for learning good heuristics, for solving hard optimization problems, and also looking at things like logistics. Right. So in fact, I'm working with a couple of teams now on looking at using reinforcement learning for solving very large distributed warehouse management problems, right? And we're looking at deploying solutions that are built using RL, right? So it's not just an academic exercise. Right? And there are other places where people have tried used RL successfully in things like combinatorial auctions, right? And learning to solve hard problems based on even when you don't have a good model of the dynamics of the world, right? Yeah, so those are domains where we certainly are looking at using RL, right? So things that are hard. So the problem with looking at this kind of supply chain management or logistics domain, when we don't have a good idea of the models, right? When there can be significant unmodeled uncertainties in how the system responds to control actions, right? It turns out using classical methods just is not feasible. So people are certainly looking at reinforcement learning based methods, and there are now building solutions that are getting deployed in this kind of spaces. Right? And then, RL can replace in some cases where people would have traditionally done A/B testing, right? So again, when there is a lot of uncertainty and unmodeled factors, people are using reinforcement learning. Right? So those kinds of domains where a little bit of experimentation is needed to discover system parameters. So RL is being used. There are more mundane applications, if you will, not as fancy as cracking the protein folding problem. But there's certainly real applications. I mean, if you really want to see a wider, applicability of reinforcement learning, these are the problems that we have to crack.
Makes sense.
Yeah.
You talked about using RL for solving warehouse management. I have a very basic question. How do you go about putting like an RL system into production? So, from the point of view I'm asking is that, so I know online training is like a big problem even in a supervised learning context, right? And
Yeah.
I'm assuming that in RL context, it would be even more of a nightmare.
Equally a nightmare, yeah.
So
whenever you say that you're going to have an online training, right, whether it is
Right.
supervised or RL or anything, right? So people who build these systems are very wary about deployment, right? So they're happy to deploy something that has been tested and tried and things in the lab, and rather than look at things that are going to be adapting online, because that's a nightmare for them for a variety of reasons. Things like liability, things like safety, right? Guarantees and all of that, right? So any kind of really online adaptive systems is going to be really hard to deploy. So in this case, what we do is we take real data from supply chain, market demands, price movements, etc., etc., and then and build simulators on which we can test these algorithms. And then once these are trained on these, then we deploy them.
I see.
At least in the case of this warehouse management problems, right? We can't put it out on the real warehouse thingy and test it. So I'm trying to evolve a process where the learning happens at a much smaller time scale, in the sense that I do some kind of batch RL, like offline reinforcement learning with some existing database, come up with a solution, deploy it, have that solution act for a while in the system without any adaptation.
The simulation.
Not in simulation, real system.
Okay.
So basically, this is the solution that I think is the best that I could get based on all the data that I have so far. Right? And then I put it out in the real system and then have it, generate more data. This time it's not adapting, right? It's a fixed algorithm where people have looked at it and said, yeah, this makes sense. Okay, you can put it out there. Okay, this is not going to cause a lot of problems. Then you gather the data that's generated by the system's performance, and then go back and try to adapt your model again. Right? Again, every time you adapt the model, it is done using batch RL, right? Offline RL. But then in between, you can actually deploy your model itself in the real world, right? Assuming that it has reached certain amounts of convergence and some kind of human agency can verify it and certify it. And then you put it out there, and then you come back and you start improving the solution. So I think for a very complex domain, right? So I think something like that would potentially work. Yeah. Sorry, you were going to ask a question.
So it's essentially like swapping the model in production environment, time to time.
Yep.
Makes sense. And testing it in the simulations during the development.
The development is, there are lots of, right now there's a lot of literature that's coming up in batch and offline RL, right? But my favorite, which I know from a while back, is this kind of fitted iterative models, like fitted Q iteration and so on and so forth. And those essentially iterate over a fixed batch of data, try to do like Q learning on a fixed batch of data, and then use that to generate a better solution than what was used to generate the initial samples.
I see.
So just the model development is also done on the offline data. It's not just the testing, but the development also can be done on this real data that's measured from the system, not necessarily from the simulator.
Got it. And how much does the simulation help you set parameters or boundaries? So essentially, when you're deploying like a supervised learning solution, you have an idea that, okay, when my X metric falls behind this range, I need to take it off and train it again, right? Like my distribution is shifted or something has happened. I don't know what's going on. Does the fact that you have like a simulation, does that help you like narrow down these parameters a little bit? Does that affect it at all, or is it like a completely separate step?
Good question. I don't think the RL community has even come to a point where they're talking about model maintenance and other things, right? In some sense, what you're talking about is like a model maintenance setup. Right? So I have a model that's deployed, and I would like to pull that out whenever needed, and then refresh it and so on and so forth. In reinforcement learning, the simulator is literally used for learning the parameters of the solution. Right. So you basically use that. In supervised learning, you have a set of examples somehow that is generated by a human labeled data or some kind of a semi-supervised setup or active learning setup, etc., etc. But then you always assume that there's a set of examples on which you are training a model. Right. In RL, if you do that, that is called batch RL or offline RL. And usually the set of examples that you need for your training itself is generated by the functioning of the learning algorithm in an environment, in the simulation environment. Right. So it's so the simulation is essentially used for doing the estimating the parameters of your solution, not just to do some hyperparameter tuning or anything. That's how classically people have been using simulations in RL. And as to the question of, okay, if I have a deployed system, can a simulation help me in this particular kind of a workflow that I was telling you, right? Pulling out a deployed model and periodically updating it, refreshing it, and plugging it back in, right? That kind of a setup, it's not entirely clear. I mean, what role a simulation can play, and I can hypothesize and what roles simulations can play here. But if you're asking me, is there a well-established notion of this? The answer would be no.
Makes sense. To segue more into your journey with RL, Professor, what was it that sparked your interest in RL when you was a grad student? Why did you choose to start working in RL rather than any other field?
Okay, so when I was finishing as my undergrad, right? So I wanted to, AI was hot back then, right? So neural networks are very hot, so I started reading up on neural networks because I really was really fascinated by this whole idea of, reading a lot of science fiction and Asimov and other things, right? So really fascinated with this whole idea of machines being like human level intelligence, right? Machines achieving human level intelligence and so on and so forth. But by the time, like in the early 90s, right? So when I was getting into grad school, neural networks had progressed to the point where the understanding had evolved to, okay, these are very efficient ways of doing optimization with nonlinear parameterizations, blah, 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 and all that, right? So, and then you start reading that and then go, come on, this doesn't sound like what humans do. I spent about a year and a half or so, reading up a lot on neural networks and working with ANNs back then. And then I said, okay, this is all fine, but this is not what I was really looking for. And then I came across a few papers that were talking about the use of temporal difference models in trying to explain how monkeys learn, like Reed Montague's paper. Right? And those like some of the early pioneers in using temporal difference learning in modeling dopamine firing in the brain and things like that. Right? And I thought, okay, this sounds interesting. So let's try to learn more about it, right? And then that's how my journey into RL started. In fact, when I started learning reinforcement learning, my advisor was not even working in reinforcement learning at the time. My master's advisor, of course, not my PhD advisor. My master's advisor at IAC, right, Satyakirti. But he gave me the freedom to explore whatever I wanted to, and he actually also learned RL along with me. And he's a much smarter person than me, so he learned faster than me. So at some point of time, I started learning RL from him. And so then that's how I got started looking at reinforcement learning, as coming from motivation coming entirely from the neuroscience side of things. Right? And then of course I went to Amherst and started working with Andy Bartow and Rich Sutton, right? And so that completely pushed me into the more AI style of looking at RL, and partly because I just never could wrap my head around biology. So we ended up doing more and more of this, right? And then during my PhD days, I started again looking at this whole notion of how humans don't learn at we don't learn at one level of granularity. So for us, we in fact very seamlessly move between different ways of looking at things, right? So there's this example that's given in the RL book about people driving. So the question is, okay, where does the agent stop, right, and where does the environment start? So when you're driving, you can think about your car, your foot pressing the pedal for accelerations and brake as your controls, right? And the amount of the angle on the steering wheel and so on and so forth. This could be the granularity at which you're thinking. The other granularity could be that, okay, do I turn left here or do I turn right here? Right, you don't worry about how much you have to brake, how much you have to twist the steering wheel by when you make decisions to go left or right, right? And the other level that you could be thinking is, okay, where am I trying to get to, right? Should I go from from Adyar to wherever, right? So Mylapore. So I'm basically thinking at that level of granularity at some point. So when I'm driving a car, I'm thinking at all levels of granularity. And in fact, when I finally actually do the actions, I'm doing it at an unthinking level where my neurons are firing and my muscles are twitching and pulling the pedals in one way or pulling the steering wheel in the other way and so on and so forth. At that point, it's actually unconscious. But as a baby, if you ask the baby to push something, it won't be able to. Even that is a learned behavior, but it's learned so well that it's become almost subconscious for us. Right? So humans are so good at learning and reasoning at these kinds of multiple levels. And so the question, of course, to ask is, how would you do this computationally? Right. So there is again, when I was starting my PhD, round about that time, the first couple of years of my PhD, there's all this work that was coming on hierarchical reinforcement learning. But then there's a whole bunch of questions to ask about how humans would internalize these hierarchies, and how do I know which part of the hierarchy is useful when, and how can I actually identify situations when I'm transferring from one hierarchy, one problem to another, so on and so forth. So there are a lot of questions to ask about what is the fundamental nature of representation that we have in our mind, and how do we identify things are similar or not. And so I started working in that direction, and so came up with all these notions of similarity, and then when one solution can work in another situation, and so on and so forth. So that's basically how I got into doing all kinds of RL stuff, and I've been doing hierarchical RL since then, since mid-90s.
Wow. Can you talk a little bit about this idea of representations a little bit? I come from a very supervised learning background, and representations to me as an NLP guy means word vector, but
Sure,
right?
sure. So
Data embedding.
Okay,
Mhm.
let's give you more. Yeah. So the way, in fact, technically, the way I modeled this was as projections, right? So all this kinds of distributed representation learning and all that is a lot more fancier, right? I mean, we didn't have this notion back then, right? So representation learning as a neural network, looking at the last but one layer of the neural network and all of those things. Yeah, those people understood back then, but so the representation in my case was, let's say that I want you to solve a problem, right? So when you're driving a car, right? So I'm asking you to, so since I started with the car driving example, let's just stick with it, right? So I'm asking you to, make sure that you're driving down the road and making a left or something. Let's say you are a novice driver, And then halfway down the thing, I ask you, okay, did you notice the color of the shirt that guy was wearing at the third lamppost?
Right.
You wouldn't know
Yeah.
because you were not paying attention,
Right.
right? So you are very focused on what are the factors, right? If that guy had actually stepped onto the road, you would have probably noted him, right?
Hmm.
Even then, if I ask you, hey, what was was that guy wearing a shoe or slippers? The guy who stepped in front of your car. You would say, what, that idiot? No, I didn't notice what he was wearing. Why should I? I was just worried about braking on time.
Hmm.
Correct? So this is what I mean by representation, right? So when you're trying to solve a problem, you're only focusing on the factors that are important, that are going to have a direct impingement on the quality of the solution that you're going to derive, right? If you had not seen the guy step onto the road, right, you would have probably hit him, right? But since you saw the guy, you're happy, but you don't really worry about what they were wearing, even though technically you would have been receiving that input, right? Your eyes would have been seeing it, but you just didn't notice it, you didn't record it, right? And humans are so good at doing this. We kind of, in fact, we are so good at even thinking that we saw things that are not there, but that's a different different issue. But we're so good at ignoring what we see, right? So this is what I mean by representation. It's at a high level, it's a meta level, right? I'm not talking about the low level representation that it's very popular now when people talk about representation learning, right? So that is not what I was talking about earlier. Of course, we do a lot of that now because it's given that the neural networks have become the substrate on which you build all of these things, right? The deep RL setting and so on and so forth. Right? It's become imperative that you have to start thinking about, the kind of a distributed representation sense for modeling all of these things I'm talking about. But if you want to relate it to the modern terminology, the closest would come to attention. Closest the concept would be to attention vectors.
How does this idea of representation or attention, how does that pan out in terms of like the actual RL code? I guess code is may not be the right way, but essentially the structure of how the RL algorithm is working.
Like
So-
how the data flows and affects the
So the
algorithm.
way to think about it is the following, right? So you have an underlying real truth, right? I mean, there is underlying world, right? But then at any point of time when I'm actually looking at the world to make a decision, right? So I'm going to look at some function phi of that underlying world x, right? So at any point of time, I give you a phi of x. So now there are parameters to the phi which could be learned by the agent, right? And it did not be a single phi. That could be a phi one, phi two, phi three. It could be different functions of the underlying world, and which I'm looking at in order to make my decisions, right? So if you think of, I mean, let's take a deep Q network. I'm not sure if you guys know about the DQN. So one way of thinking about a deep network that learns representations for RL is the fact that all the layers of the neural network except the last but one layer, right, are essentially learning this phi function that gives me a representation. And then I feed that into the last layer, which is basically learning some kind of a linear function approximator with the softmax on top of it. That gives me whatever is the final output that I want. Okay. So learning that phi is essentially what the representation learning would reduce to. And depending on the various kinds of tasks that a single agent is looking to perform, you might want to learn different kinds of representations.
I see. And then you could have like multiple networks all feeding into one linear softmax layer, or essentially would every be represented by
everything
one
that I
subnet?
did was pre-deep networks, right? I mean, all those
Right.
old work that I did were all pre-deep network. If you want me to put that in the deep network setting, yeah, sure. All of these could potentially have a single body and multiple heads, right? And each head is being specialized to a different task, right?
Task.
But sometimes, you might not just a single layer in the head. You might want to have multiple layers in the head so that you can condense the signal even further. right? And other cases, I'm not a huge fan of end-to-end training. Right? If you can get it done, that's great. But I think typically when people, too focused on end-to-end training, they tend to ignore a lot of domain information that's available to them.
Right.
So if that is a way to, inject that domain information, saying, okay, hey, if you're going to be solving this problem, I know that these are all the features, that these are all the parts of the input that you don't have to look at.
Right.
Right? If that's the way that I can inject that into the model, right, easily. Maybe there is a masking function that I could do, or other things, right? I think that would be a better way to do this than say that, okay, there's a single body with multiple heads, and then a lot of shared neurons, etc., etc. So, I mean, it's not that people have completely thought through what is the ideal neural architecture for hierarchical RL yet. Okay, everything that is out there is pretty naive, in my opinion. All the hierarchical RL architectures out there are pretty naive, but many of them do use a large shared network with multiple heads. But I think there's a lot of work that needs to be done there.
So, taking a step back, since you've been involved in the field for so long, can you tell us a little bit about what were the dominant approaches before deep RL became such a big thing? Obviously, you would have some sort of function approximator that your agent is exploiting, right?
But more like some landmark moments in RL, if we put it like that.
Holy cow! What are the landmark moments in RL?
Like if we look at, if I can give you like a deep learning, maybe parallel, like the back propagation happened, and then we figured out GPU can be used, and then ImageNet happened, and the deep learning paper came in 2006.
My God, that is a major condensation. So from after 83, it was 2007.
Yeah.
Okay. I don't know what condense seems that way, right? I mean, that's sure. So if you want me to think about it that way, right? So then the 83, temporal difference learning was proposed, right? So that was a huge. I mean, that's kind of the start of the field of RL, if you will. Then the next big step would be what's called Q-learning, right? So this is proposed by Chris Watkins, and that was in 89, if I'm not mistaken. And so the nice thing about Q-learning is that not only was it a very convenient algorithm that can be used for completely model-free RL, but it also had the one that really formalized the connections to MDPs and operations research and so on and so forth. Right? So that kind of completely changed the way you looked at reinforcement learning. Instead of looking at it as being motivated completely from behavioral psychology and trying to solve some kind of secondary conditioning problems and so on and so forth, you kind of now start looking at it in terms of, oh yeah, okay, here is this MDP, and then you have these value functions, and then you're trying to learn these value functions by drawing samples. Let's give a completely new way of looking at RL, right? So that's something that happened with Chris's work, and I mean, I have a personal bias towards looking at the hierarchical RL part, right? That came much later, right? In like mid-90s. Right, and so in between, the reinforcement learning was looking at a variety of different things. Right, so we learned to do better sampling, and there was 88. Williams came up with this policy gradient approach. Right, so that that kind of laid the grounds for a lot of gradient-based RL approaches later. Right, but that was one of the major events back then. And then there was all these results that were coming out that letting us understand function approximation and RL much better, right? For example, in '92, there was some work that talked about, looking at eligibility traces and Q-learning and showing that you can do control over longer time horizons. And then I think one of the key landmark things was the '96 paper by Ben Van Roy and Tsitsiklis on function approximation and RL, right? This is the first time people actually tried to show something formal in terms of, okay, linear function approximation with reinforcement learning will actually work. But there are some caveats, right? So, and then people didn't have a good handle on how to do this with control, and then the early results on function approximation with control came in like early 2000s and so on and so forth. And then you had the deep RL, the DQN paper. In fact, there are a lot of small innovations that led to the DQN paper. DQN paper didn't just come out of the blue, right? There is this neural fitted queue, which kind of hit almost everything of DQN except the convolutional network. Right? And but that kind of made it really big, right? So this was I think 2014, right? And then you have this whole slew of deep RL breakthroughs that are coming after that, right? So you have the Atari thing that came, and then AlphaGo, and then the StarCraft solutions, and then the London Underground navigation kind of thing, which didn't use RL that much, I suppose. And then you have this AlphaFold, right? And all this modern things that people are doing with RL and robotics and all of that, right? So all of these have been condensed into the last 5-6 years, right? But a lot of very interesting developments that happened in reinforcement learning along the way. I might have forgotten some, and but yeah. So I think I hit most of the highlights.
Right.
Of all, yeah.
As a follow-up, so you a lot of your work has been in hierarchical RL, right?
Yep.
What do you find to be the most exciting things about RL today? Like, where do you think the most interesting avenues to be looking at are right now, or like, what are some research gaps that you think desperately need to be filled in the RL space or for the RL community?
So, I mean, we already spoke about one of these, right? So the whole deep neural substrate for doing hierarchical reinforcement learning, right? It's not quite there yet. So I don't think we have a good deep hierarchical RL framework yet. And I mean, a lot of people are working on it. I think we'll get there soon. But there seems to be a lot of challenges in solving that, right? So that is one big challenge that we really need to address. Another that I mean, a lot of interest in the community is on looking at this offline RL or batch RL approaches, both in terms of getting it to work with more complex robotics problems, where really getting the online setting to work is hard. And then there is a related problem of getting all this reinforcement learning done with assumptions or simplifications for the simulations, and then getting it to work on the real world. So what they call as a sim to real problem, right? So that again is a big challenge. In fact, partly to address the sim to real problem is what they are doing with the batch RL, right? Instead of saying that I'm going to simulate the environment, why don't I just take the experience from the real environment and then build these offline models? So that is another big problem. And the third, which I am very keen on, is that if you think about how we do problem solving, how we do reasoning, right? It is not that at all levels. I talked about multiple granularities at which we'll be doing our representation while driving a car, but it's not like that all levels we actually learn, right? I don't learn how to get from Adyar to Mylapore, right? I mean, I know a map and I can look at it and I can plan it and figure, okay, I go like this, I go like that, I get there, right? But the learning is more in terms of, okay, how do I steer the car? I mean, how much should I press the pedal in, right? All of these things are things that I learned, right? So learning is at some sense a slightly lower level in terms of the time scales of problem solving, right? And at the higher levels, right, I start using some kind of symbolic representations and then start doing planning, right? So there is this continuum, right? So at some point you're in the kind of whatever is the symbolic space we're talking about. I mean, it's talking about symbolic is now becoming loaded, but so whatever kind of symbolic representation I'm talking about, right? So at that level, doing more deliberative, like people are talking about all the system 2, system 1, all that, right? But I'm thinking of just doing planning, right? And then going down further and further down in the hierarchy, and then you get into more reactive instances where you're doing pure learning, right? And how do you actually combine, come up with a nice architecture where you can look at different kinds of reasoning and learning and tying it back to a neural substrate, because at the end of the day, I think uh, a lot of people are just going to come back to that, right, as your universal representation for doing all kinds of AI and learning and so on, because at the end of the day, we have the inspiration in our brains, right? But even before getting to the neural substrate part, we still have to look at this more carefully. Right? So there have been papers out there that say, oh, combining relational representation and reinforcement learning, and even there have been papers on doing this in a hierarchical fashion. But I still think they're all missing a lot of uh, nuances in how we do these things, right? So that we should really worry about putting it back in there. Right? So these are, I mean, like three directions, but not by no means the only directions that are interesting in RL right now. The three that are personally interesting to me.
Right. Actually, I want to pick your brain about this third one a little bit more, because I'm not sure I understood it. Essentially, what you're saying is that there are many different levels in which, say, a human would make decisions or learn, and we don't have a good understanding of how agents reach those same decisions or learn.
So, well,
Or am I
so
mischaracterizing what you just said?
slightly. So what I'm saying is, so humans are very good at using different kinds of reasoning, different kinds of decision-making systems at different levels of granularity, and we're very good at passing information back and forth among them.
Right.
Right. So in the AI world, we probably have a good handle of how to use each one of these decision-making paradigms, right? But then when I start talking about handing information back and forth between them, and then using what method to solve when kinds of issues, right? We don't really have a good handle of in the AI system right now, right? AI community right now. So that's what I'm talking about. Not that we don't know how humans solve problems. We don't, but that was not the point of what I was saying. But the point was we should have a architecture that allows you to smoothly pass information up and down the uh, hierarchies, but with different kinds of solution mechanisms across different levels.
I see. And then you envision that a neural architecture would be able to do this, or
Eventually,
do you think we need to like hit the drawing board and come up with something different?
eventually, I suppose that something like a neural architecture should get there, right? I mean, neural architectures are doing a lot of things which people didn't think they will be able to do back in the 80s and 90s, right?
For sure.
So maybe something, but yeah, maybe once we have a better understanding of how our neurons work, we'll have a better computational model for the neuron. Yeah. But even before we get to the neural architecture, the point I was making was we don't even know how to do this even in the symbolic setup.
Right. Makes sense.
So
Yeah.
in fact, I can expand on that a little bit and tell you about some recent work that we are doing, since you have spent so much time on it.
Sure.
Sure.
So we have been looking at, so this is in collaboration with Sriram Natarajan from UT Dallas and Prasad Tadepalli from Oregon State. And so we have been looking at this question of, hey, I have a hierarchical planner, right? But then the hierarchical planner, typically the way the hierarchical planners are set up is, you have different kinds of methods that execute certain actions in the world and achieve certain goals, right? And then you have the hierarchy, right? So methods at the higher level can call operators at the lower level, and the operators do things in a more finer granularity. They pay attention to more clauses, more attributes of the world, while the methods do something lesser. And then you keep going down, right? So methods could call methods, those could call operators, which finally make changes to the world. Right? So this is kind of a hierarchical planning setup, right? So what we have now is first attempt at an architecture where the methods are pre-specified for you, but then the operators themselves are not known fully, right? So when the methods start reasoning, they come to a point where they have, they know that they need an operator because they need to actually change the world to go from one point to another. And at that point, they learn the operator. But the information that is passed down to the operator is essentially not only what is the goal the operator has to achieve, but also the attributes that are most likely to impact what the operator has to learn. Right. So in some sense, I pass you the representation that I was talking to you about, right? So the planner not only plans what should be the goal for the RL agent to learn to solve the bigger problem, but the planner also kind of determines what should be the approximation, right? What should be the abstraction level that the RL agent should be looking at to achieve that goal. And so it gives it to the RL agent. Now, the advantage of doing this is because the RL agent is looking at a very, very small part of the input space, right? When I'm trying to solve a slightly different problem through this whole setup, the RL agent is already, learned for solving this new problem because all the irrelevant information that has changed, right, is not being passed on to the RL agent. So, for example, if I just say that, okay, I have to take a file from one room to another in an office, right? I have to plan how to do this because I know the office layout. But then that might be an operator that says, okay, pick up the file, right? So that's the only thing that I'm learning, and I don't care about where I go and whatever, right? So if I learn first to go from room 1 to room 2, right, and now take the file from room 1 to room 2, now I have to solve the problem of going from room 5 to room 7 with the file. I might have to replan the solution because room 5 and room 7 might be connected in a different way. But I don't have to relearn how to pick up the file, how to open my hand, grasp the file, and from a robot point of view, because I already learned it when I did the previous one, only because I had ignored the fact that the file was in room 1. Right? And the fact that I could ignore the fact that the file was in room 1 is actually told to me by the planner. The planner says, oh, what I really want you to do is pick up the file, and at the beginning, the file is on the table. At the end, the file is in your hand. The fact that you are in this room doesn't really figure in anywhere. So go ahead and learn. So that's the nice thing about it, right? Because the whole question of figuring out what is the right abstraction to learn on, right? I was telling you something which I have been thinking about since my PhD days, right? It's kind of decided for you by this plan.
Right, because only the planner cares about that. The agent will only learn like the set of composable actions.
Yep. Yeah.
I see.
Actually, this is pretty hot off the press kind of thing. It's under review still. So.
I mean, thank you for sharing that with us then.
Yeah. Okay, so moving on to maybe some more general graduate studies related question. One thing, and this is not like a question, a series of questions we want to dig you through to get a better understanding of maybe the problem picking and finalizing process. So let's say if a brand new PhD students come to you today, what would be some interesting directions you would try to point him to? What would be your starting instructions to him or her? And then maybe we can dig deeper into this.
Okay, so I mean, if a PhD student comes to me directly, I mean, I would be pointing to something interesting in RL or in graph, and learning on graphs, right? In graph neural networks and things like that. Those are the two areas that I'm doing a lot of work in more recently. But in general, right? So I would basically point the student to perhaps a couple of problem domains which I think are currently interesting. Right? I mean, we're talking about at a PhD level, right? Not at a master's.
Yeah, we are at a PhD level, so we know at least we have a time horizon of a couple of years to solve the problem.
Yeah, exactly. So I'm not going to talk about a master's by research student who should probably be pointed to a more concrete problem, right? Saying that, okay, here is what I think you should be working on. Go, pick up references and start working on it. For the PhD student, I would probably say, okay, these are 2 or 3 topics which I think are very interesting, right? In fact, for one of my students, I did that. I said COSL RL seems to be very hot now, right? And that is one area to look in. And the other one could be this kind of offline RL solutions, because he wasn't too keen on looking at hierarchies. Okay? And then I said, okay, if you Causal RL, if you get something interesting, then maybe we can look at hierarchies. And then he went away. And what I really would like people to do is do a lot of reading. Right? Your first few months, right? You should be reading at an insane pace. Right? So when I tell people that in my first year, in my masters, actually, I don't have a count of it normally, but it so serendipitously turned out that at the end of my first year in my masters, we actually wrote a survey paper on reinforcement learning. So I know exactly how many papers I read because we cited all of them, at least the lower bound, right? And my first year, I had read 140 papers. Okay? And I tell people, they go, whoa, 140 papers in a year. Right? Okay, fine. Okay, let us not aim so high. Can you read 3 papers a week?
Makes sense.
That's manageable. And that's basically 150, right? But you just have to keep at it week after week. And if you goof off for a few weeks in between, you'll end up with 140. So it's not as daunting as people think it is, right? And in fact, 3 a week is actually very low when you're starting your PhD.
Right?
I would say that you should be reading 20 a week. Right?
Sorry,
you
what?
You should read two papers a day. Okay.
Yeah.
I mean, what are you doing? What else are you doing with your life at that point, right? So, I mean, there's nothing like reading to get you started on a field, right? I mean, there's no osmosis that's going to happen, right? So I mean, reading two papers a day is very hard when you start off, right? Doing 2 or 3 in a week is a good thing to get to. But after a while, right, after you have been in the field for like a year and a half, you are going to see that you can read 2 papers a day.
Yeah, that makes a little more sense.
Right. So at that point, you'd probably be reading two papers a day. In fact, when we were in grad school, right after an ICML or a NeurIPS happens, right, we will be doing this. Right? People will be just poring over the proceedings and looking at all the papers that are of interest to the group, and then we'll be reading it and discussing it in the lab meetings and so on and so forth. Right? I mean, it's very hard for you to do that first. Reading your first paper, it'll probably take a long time, right? But then your third year in your PhD, right, you're very quickly scanning through these papers and then going to the lab meeting and giving a summary of these thesis papers, and then say, okay, maybe we should pick 2-3 papers and spend more time with it later. So read a lot, right? So, but then completely, undirected reading is also going to be something very difficult, right? So this is why I like the PhD clinic idea so much. So what they are doing now, right? So PK's initiative. So you're getting all these people to come in. So you come there and you talk about various things that you have looked at, right? And then people giving you gyan. I think that's a great idea. But so getting back to what I will tell students, right? So basically, I'll point them to 2 or 3 interesting directions and then ask them to start reading some papers on it. Right? Dig deep. So this gives 2 things. It gives them an exposure to the different problems that people are looking at in the field. The second thing, it gives them a training to read papers and present ideas and figure out what is interesting in that. And then at the end of the day, so in fact, it happened with one of my PhD students that I said, let us do work on either, I'm interested in looking at hypergraphs, right? And here are a couple of things that we have already looked at in the group. Then you can probably build on top of it. Or I'm interested in looking at multi-layer graphs. So go read up on both and let's see what direction we want to take up, right? And look, we can come up with interesting problems in both. And then he basically started working on both. And he actually has interesting results on both now. So we have a couple of papers already out on hypergraphs and maybe 1-2 papers on multi-layer graphs, and we're writing one more and we should be done with that. But there are some things that we were stuck with. One my former master student wasn't able to solve the problem. He read it and then he wrote a paper. Worked with some other people in the lab, and then they managed to get around some crucial difficulties that we were facing. So completely undirected reading is hard because you don't really know what is a promising direction to read it. You might read on something for like 6 months and then find out that people have solved all the easy problems there, and whatever is left is too insanely hard for you to solve on your own. So directed, this little bit of push from the guide, right, and read. And other thing, I think I made this point earlier in our chat with PK also. I did mention that you have to talk a lot to your lab mates, your peers, right? If you don't have a large group in your organization, that becomes hard. And that's one of the points I was making about Indian academia, is that our peer groups are very, very small. But luckily, world is getting smaller. So, and people are happy to talk and help. There is this whole openness in the ML community, which is very, very nice and refreshing. I don't think any other community puts out so much software, right, for other people to build on top of their work.
Yeah.
And
Sure.
so you could reach out to people and talk to them about their work and other things, right? So talking a lot is something that you have to do, and don't. I mean, as a matter of routine, right? I wouldn't advise picking up a problem on your own and working on it for your PhD. Do talk to your advisors, right? Once you've identified what you think are interesting directions, right? So your advisors got there because they have a lot of experience. And so go back to them and tell them, hey, look, these are what I think are interesting directions to explore. What should I do? Which one should I
So,
do?
expanding upon that, the idea of so when a student has spent some time doing the directed reading, and
Yep.
there is the cycle of between you and the student to filtering out the problem. What kind of filters are you using to, let's say, narrow down? So maybe the capability of student itself, the time horizon of the research, of course. Yeah, what filters you are looking at? Do you have like a quantitative way to define that process which people can use to filter out problems once they have some?
That's tough. Okay, there are a lot of factors that go into play here. First thing is my sense of, right, what is the capacity for us to make a contribution in that area, right? And that is something very diffuse. I mean, it's not something I can quantify. I can't say there's a very algorithmic way of doing it, right?
Yeah.
We start discussing this, and sometimes just things click, and then we say, "Oh yeah, I think there's a very interesting direction to explore," and then we start going down that path, right? And so that is very hard to quantify. And of course, the student's interests and the amount of learning the student has done certainly figures into it. In fact, I might tell the student, "Okay, it's a very interesting direction to push in, but your math skills are not strong enough to do anything interesting here. Maybe we should look at something more implementation oriented." And
Makes sense.
those kinds of factors also figure in there. And I also work a lot with the industry, right? So sometimes the problems are really interesting problems that come up in discussions with industry collaborators, right? And at that point of time, we basically say, hey, look, I think this is a problem which none of the existing methods are going to solve. So let's buckle down and try to solve this problem. Right. In such cases, the whole thing kind of gets slightly inverted, right? Instead of reading the literature and trying to find a direction to move on, right? So we are now coming up with a specific problem to look at, right? And then we are exploring the universe of ways of solving the problem. Right? And that also leads to pretty interesting research at times.
Makes sense. So,
so I can tell you there is a written down algorithm that I would use for.
So you said something about you gauge the ability for your group to make a contribution in that area or in that field, right? I guess a related question to this is, how do you gauge the impact of a contribution, right? So I think everyone wants to be doing impactful research, and people tend to have very different ideas about what impact really means. It could just be like citations, it could be like getting published at a really good venue, it could be something that is read a lot. And I'm sure you have your own definitions. Can you talk a little bit more about what to you constitutes impactful research, and maybe how you select for those parameters?
Okay. So when I say impactful research, right? So getting published in a very good venue is a great way of measuring impactful research. but it's good in only one way. I mean, if you get published in a great venue, then it's impactful, possibly. But if you don't get published in a great venue, it doesn't mean that it is not impactful. So for me, impactful research is, uh, you know, solving something which the community has been trying to solve, right? Or which the community is not even aware is an interesting enough problem to solve, right? And doing it in a fashion that kind of improves your understanding of the field. You can just look at something and say, yeah, finally, I know why all these things didn't work. That also is an impactful piece of work, right? Whether it gets accepted into Europe's or not. I mean, if you're going to get if your impact is completely going to be measured by those quantities, right? And then it becomes very hard to live a satisfying life because there's so much noise in all of those. Okay? And so, as long as you're doing good science, you should be happy with what you're doing. So now, going back to the question of how do I gauge if there is a way of getting good, if my group can make an impact, right? So it's going to be colored quite a bit by what is it that I have personally read, what I have personally come across, and I mean, so this when I say I, it also is like the union of all the students who are working in the lab at that time who would have presented various things in various group meetings and whatever I have managed to internalize, and whatever the new student who wants to pick up is able to convey, right? And at that point, if you are able to identify the direction, the gap at which that we need to address, right? And then we feel that there is a non-trivial way in which this gap can be addressed. It has to be something that actually makes a, for at least for us, gives us an aha moment. It can't be something,
Right.
oh yeah, we know how to do this. Here is this, very procedural way of solving it, and then you get this new guarantees, and you're all done, right? So it can't be that. It can't be just saying that okay, it's a hard problem, yes, but all you need to do is tune hyperparameters and resolve it, right? There has to be some kind of a little bit of an aha thing for us, right? And then we say, oh, okay, cool. So, for example, one of the aha things that we had recently was, trying to come up with some kind of a null model for, hypergraph partitioning. And whatever we came up with, we have not seen anywhere before, right? And then, it says, hey, look, this is really interesting. So when we started on the work, right, I knew that there was no null model for hypergraphs back then. It was like 5 years back, right? So for us, cracking that, right, for hypergraph partitioning, trying to see if we can get a null model would have been great. In fact, it looked like there were a bunch of people who are working with us on the same time. And when we finally presented the paper, there was another paper in the same session that was presenting a null model for hypergraphs. But the point is, we knew that there was this gap, and we knew that we had some approaches that we had done in the past, right? And there was a way of trying to contribute to that. So that's the way that we would decide. Right? This is not something that my student could have made it alone, because I was aware of the previous attempts that we had made in our group, and I thought that we were close to making a breakthrough. So we went ahead and pushed in the direction.
Right. And
So
sorry.
It's frankly, to tell you, it's not at a science, right? Part of it is more intuition and
Experience.
as one of my teachers used to say at UMass, right? More seat of the pants than a formal algorithm to do this.
I see. So I think going back to the point where you're encouraging your student to read a lot, and you're getting them into you're basically you're giving them these directed paths to say, okay, go out, see what's been done. And now you're like unifying that with your own experiences and your own background from the field and what you've attempted before. How much of that goes into telling the student, hey, I want you to come and like read this specific set of papers that where we attempt to do XYZ? Or is that more in the sense of, well, you're expected to know this already because you've already been reading in this direction?
You were asking if I would actually hand my student a set of papers to read, as
Yeah,
opposed to
effective.
letting them do the exploration by themselves.
Yes,
It,
essentially.
it varies, and it depends on if there is a area in which I have been reading a lot, or our group has been doing a lot of work in the past, and they have been reading a lot. I would hand a stack of papers mm, to the student to read. Right. In other cases, uh, in fact, that has not happened. I mean, most often we point students to starting points with stacks of papers to start reading on. Right? And of course, there is another whole different category of students that we didn't talk about. I'll come back to that later. But yeah, so we do end up pointing students to at least a few starting papers. So, for example, the guy who's going to do causal reinforcement learning, I point him to some of the papers on causal bandits that we have been reading, and then he started from there, and then he has been now he has read. In fact, he's more up to date with the literature than I am right at this point. So it's not a question of just saying, okay, here are a few keywords, go read. It's more often than not, okay, here are a bunch of things, go read, and if I think that among the directions I'm suggesting to them, if there is a direction which we already explored and not made much progress on, or we are making progress on, and I want this person to take it to the next level, I would suggest those papers as well. But I don't. I'm not a huge fan of saying telling a PhD student this is what you are doing. I would really like them to get I really like to get the buy-in from their side.
In your group, do you push for any sorts of like knowledge transfer between teams outside of papers, or is it more just
No,
like
no,
you
no.
already explained?
We always point people to, hey, look, you're going to read this thing. This guy has been doing this stuff. Please go talk to him also. He can tell you, give you more gyan. Or somebody comes and gets stuck in some problem. I say, look, I know that person has actually tried to solve this in this version of the library. Why don't you talk to them? And so all these kinds of knowledge transfer happens all the time. In fact, even after students graduate and leave, we still drop them in to do this knowledge transfer. So yeah, so that happened. It's not a question of just reading papers or writing papers together, but it's really nice to have a group like that where you don't have to solve every problem from scratch. That somebody is already willing to impart knowledge to you. Was that the question that you asked? I mean, I'm not
Essentially,
sure.
yeah.
That
I was trying to understand basically.
that seems like the most natural thing to do. So I wasn't even sure why there was a question. But,
Fair enough. I was just trying to understand essentially if you have a process in place for ensuring that this happens, or if there's a way that.
ensuring this happens. How can I ensure this happens? Okay, so the only thing I can, the only way I do this is like whenever I think there are people working on something similar together, I call for a joint meeting.
Fair
And
enough.
then I get them to sit and talk with me, and then then at least I know that the initial conversation idea exchanges have happened, and hopefully they will follow up on that, and then we will have other meetings, and then maybe we'll work on a slightly different direction involving all these people. Yeah, but I'm not a great cop, so I'm not good at keeping tabs on whether these guys are actually working on what I told them to work. I'm collaborative things like that. It happens organically. I mean, I've never had too much of an issue in saying that, oh, I asked these two guys to work together, they don't talk to each other. So I was telling about this other category of PhD students who I've been getting a lot of, right? These guys come in knowing what they want to do.
Ready?
Right?
Like before they start the PhD.
Before they start their PhD, there are people with some experience in the industry, or people have been working in research labs, right? And then they come and saying, "Hey, look, I have this really hard problem that we have been looking at for the past 3 years, and I don't think I'll be able to do this working alone. Can I join you for a PhD, and can we work on this problem together?" So I've had people come in like that. So yeah, those guys are really nice to work with because they know everything. They are very focused on what they want to do.
Interesting.
Yeah.
So are these a lot of times like part-time industry people doing PhDs, or is it like students, you see a lot of students also like this?
Mostly it has been either part-time people or guys who are just doing a master's with us, saying they're getting very excited about this problem and then they're transferring over to PhD and
So
continuing that. But if people coming from outside have mostly been people from the industry.
on to that last part, the master's part. What do you like? What are your thought about this? Because I think these are two different things. Somebody working in industry or maybe like in a research lab has spent years on a problem, versus the same thing with masters, that maybe you do your master's thesis on something, because this is something I have seen happen. You do your master's thesis on something, typically you are investing 6 months to a year maybe in doing that, and a lot of things look very interesting, very hunky-dory at that point, and that this is the problem I want to solve. But I guess when you sign up for a PhD and now you want to do it for long term, like at some point you realize that problem is maybe not the way you were understanding it.
Sure.
So how much, like, when a student like this comes to you, you are thinking about it that, okay,
100% of the time, it's a student who's already working on the master's project with me. So
okay,
and
makes
I know
sense.
what they're thinking about and what direction, what are possible directions we can go ahead. And unless I'm convinced that they can do it, just don't take them
You
on.
would tell them not to. Yeah, makes sense. And maybe to segueing this into the grad school discussion, and now this is even like much abstract of a question than even like just how to pick problems. Uh, See, especially in like IITs and triple IT here in triple IT Delhi, a large part of students who are with us researching is RAs and BTech students who are mostly like, okay, I'm going to do this, get a paper, do the GRE, move abroad for grad school. Uh, so what are your thoughts in, like, you have done your grad school abroad, of course, and you have been mentoring students for in India for years now. So
I did my master's in India, so which is also part
yeah,
of grad school, right? So
yeah. So what do you think are like trade-offs versus like benefits of doing like a grad school abroad versus in India? And like, if a student is today trying to make their decisions, what are the things you would ask them to focus on, like think about before they can make that decision?
okay, so yeah, things are very different now than it was in the past, right? So, but so there are a lot of factors that go in, right? I mean, there are a whole bunch of personal factors that play a big role, and so putting aside those personal factors, right? I mean, financial circumstances, family, not wanting to travel, etc., etc. Putting those aside, so I would say that the top schools in India, right, in the areas that you have good faculty in. In fact, if you know that even when you're applying to the US, right, even in the past, people used to say, I mean, you can go to the really top schools, or if you know who you really want to work with, right, then you can go to a second tier school also because you're going to work with them and can produce a lot of good papers and so on. So that's the right thing to do. So if you should be looking at the advisor, not necessarily the school. Right? So the similar kind of advice now applies to here. And there are a whole bunch of other questions that I would have said in the past about not being able to travel to conferences, being cut off from the world, etc., etc. But that is no longer true. I mean, most of the
Yeah.
top schools, right? It's very easy to get connected abroad, and you can go visit people. Everything is becoming easier and easier, and the government is also pumping in more money into this kind of international collaboration. So those things are changing, right? So ideally, I mean, the question then boils down to, okay, if you're really good, right, and you want to do a PhD with a good person, and there are enough good people in India, right? So if you get into the right school with the right advisor, go for it. Shouldn't worry about whether it's in India or outside right now, right? But then, uh, yeah, if you're not really sure and you want to explore a lot of areas, so ecosystem hasn't evolved to a point like a CMU or a Stanford or something where you can go in and then have like Hajar faculty to sample from and look at all kinds of research that is happening, and you have like 100 faculty who you'd be happy to get your PhD with, and so on. So we are at the top Indian schools, I would say, are at the second tier your schools, like that, not in the top 10, not in the top 20, not 50, right? Maybe in the next 50 kind of your schools right now. It's sad, but we are much better than where we were when I was looking for a grad school, or when my master's advisor was looking for a grad school. Right? So I would say that you should look at what areas you want to work in and see if if the right guys you want to work in are around here, right? And then go with that. Right? And of course, there are a whole bunch of other things in India. I mean, you get some scholarship, right? So you don't have to worry about getting an RA. So funding and other things are easier in some sense. Of course, the volumes are not that high, but you also have to adjust for the cost of living. But good students, right? We now have sufficient amount of scholarships, right? Whether it is the PMRF or any of the other kinds of supports that all the various colleges give people, right? You don't have to worry about settling for 20K, 25K scholarship or something like that. You get a lot more. Of course, certainly not in the foreign country levels, but you can still think of something of the ballpark of 70, 80K per month. So all of these factors, I mean, shouldn't figure in, but sometimes it does. So I would go back to my recommendation, right? So pick. I mean, if you have an interesting advisor that you would work with in India, work with them. Right? If you think that, oh yeah, there's nobody here, I really want to work with this other guy, then you want to go there.
Okay.
I'm assuming that if you say that you're going for a PhD, you know what area you want to work in, right? If you're completely clueless about it, think twice about
doing the PhD.
Yeah,
for sure.
But then maybe go to a school which has a much more broad base, right?
Right. So given that labs in India tend to be a little bit smaller, they may not necessarily have like the publication footprint that lets people find out about them very easily. So do you have like any advice for people who are looking for like advisors? What are some things that they should be like looking out for or something like that? Because I mean, in an ideal world, I would be able to like open up CS rankings and see IIT Madras number 3 or whatever, right? But we're a little ways off from that.
Yep.
So do you have like, rather, okay, what are some routes that students have taken to find, for example, you in the past? Right, since you're getting a lot of students who are very, very focused and very interested in what they want to be doing.
Holy cow, man! That's actually tricky to answer. In my case, almost everybody who joined me kind of knew me before from various circumstances, right? So it is not like they did a blanket search on Google or something and stumbled upon me. And, no, but it's actually so. I haven't thought too much about it, right?
Like having a system like that would make grad schools in India more appealing to students?
Yes, for sure. Yeah. For sure. I mean, I really like the thing, right? So it's like, see, we have certain like India events, right? So like ACM has this ACM India event, and then you have this various conferences that happen in very, very niche areas, right? But then if you look at it, right, it's not really showcasing Indian research. Look at ACM India, right? There is some amount of work that happens, but the big ticket speakers who are all advertised are all people from outside India. So we don't have a huge culture of celebrating our own people. And Yeah, this is something that we have to think about. Maybe at least for computer science, maybe something can be thought of. But that's an interesting question. So how would a PhD student who is interested in a specific area find out without publication counts and things like that helping them along? But then, come to think of it, right? I mean, there are people who are very good in publishing in a specific niche areas. I mean, if you look at CS ranking, it has introduced the India specific ranking now, right? So if you go there, but then CS ranking is pretty limited, right? They are very coarse grained in some of their areas and too fine grained in some of their areas, and
Right.
so it's like all over the place, right? So some of the really good venues are not covered by CS ranking. So somebody who publishes regularly, for example, in a multi-agent systems conference, will never get ranked in CS ranking. So, so there are no perfect solutions like that. But
Got it.
there should be like a national directory of faculty or something like that, which
Yeah,
is maintained by some organization.
because this is how I think about it. Even being like a grad student if you're in a grad student in one of these institutes already, you still have like a network to reach. You start knowing people you through talks or via your professor and a lot of things like this. But like if I think about myself, before I got into this ecosystem of Triple IT Delhi, before that, when I was an undergrad in like a small private college, and maybe a lot of it coming from like my ignorance of being going out and looking hard enough, but the knowledge of what's happening around and the academic circle of people approached to was very limited. And more than that, I never even saw a lot of people doing it very actively. And I guess that is something which more accessibility can change.
Yeah. See, one of the things that I used to do a lot, right, when I started off here, right, I used to go to these second tier and third tier colleges a lot. I mean, and give talks, right? Talk about how to do research. Talk about basic tutorial topics. Talk about something cutting edge, depending on how ready the students were, right, at different levels. But I used to do a lot of these talks. Right, and partly because of that, I was actually beginning to get some good students from these colleges. Right? So that was one way of doing this outreach, but these are not scalable methods, right?
Yeah.
Because the number of colleges are too big. And I used to go to the specific colleges I knew were good, and then maybe not with one visit, right? You visit there 5 or 6 times, and then give various talks, and then you start getting good students with them. Right? So yeah, but given this era of people being able to do things so easily online. And I think we should start some kind of initiative. There is some small bits that are going on. Some universities, some colleges are now started recording like this 5-minute YouTube videos and putting them online about faculty research interests and what they are working on and why it is exciting and so on and so forth. And maybe we should do more of that more systematically. And publicize it, right? And saying that, hey, look, here is this portal where you can go and find out about all this faculty in doing research in India and whatever areas you are interested in.
Right.
Right, and have ways by which they can. It's actually easier for you to find out what people in
what people are doing.
Second tier US school. No, I'm saying it's easier for you to find out what somebody in the second tier US school is doing. By second tier, I mean somebody outside, say the top 20. Than it is for you to find out what somebody in an IIT is doing or a triple IT is doing.
For sure.
And that's sad. Yeah, I agree. I mean, that should change, but I don't know if I have a magic solution off the top of my head for that.
Makes sense. I think we're mostly out of time.
We're past time.
Yeah.
Thank you, Professor. This was really nice talking to you.
Thank you for the thank you for the questions also. They actually set me thinking. Yeah.
Thank you for listening to the ML India podcast. Your hosts were Hitkul and Karmanya.